Okay, welcome everyone to the online Horowitz seminar. And today we're very happy to have Tyler Helmuth from the University of Bristol to tell us about random spanning forests and hyperbolic symmetry. Thank you for coming, Tyler.
Thanks for the invitation. It's good to be back, although virtually. It was about 2 years ago, I think, that I was in person.
Yes.
But then we were, able to share a melon together and everything. It was much better than this. But
break your own melon.
That's right. Okay, so this is about random spanning forest and hyperbolic symmetry. It's joint work with Roland Bauerschmidt, Nick Crawford, and Andrew Swan. And the first thing I'm going to do is change the terminology from the title to what I'll use in the talk, which is this thing called the arboreal gas, which is a type of random spanning forest, but because of the multiple uses of this term in probability, I'm going to try and stick to the new phrase arboreal gas. So what is it? You take some finite graph, G, vertices and edges, V and E, and you take some parameter beta, which is going to control how many edges are present. And you take this very simple thing that you declare the probability of some forest F to be proportional to beta to the number of edges contained in the forest. So this size of F is the number of edges. Okay, so every forest with K edges appears with probability proportional to beta to the K. And if you want, you can rewrite it in terms of this quantity P beta, which is beta over 1 plus beta. So this rewriting in the second line is just pushing symbols around. So there's sort of 3 origin stories for this model, 3 ways it can arise, and they're all interesting to think about. So the first is why I made this rewriting, is that if I take bond percolation with parameter P beta and condition on the event that the open edges form a forest, then you get exactly this arboreal gas measure. So that's one way that this model of random forests can arise. That's a slightly weird thing to do. Why would you condition percolation to be a forest? But it's something you can do. Another way it shows up, and this is sort of better known in the literature, is that if you take the random cluster model, so meaning percolation weighted by Q to the number of clusters, and take Q to 0, so take the random cluster weight to 0 with the edge probability being proportional to Q, then you also get the arboreal gas. So this is another origin story. And the last one is one that is almost certainly new to you. It's also a graphical representation of something called the H02 spin model. And this one we'll see later. Probably you've never seen it before. Okay, so I think for this talk, I'm mostly going to think about the first version and the third version. But the second version is also interesting, although it's just harder to turn into theorems, or use to turn into theorems. So for the main question, I think the perspective of the bond percolation is the most useful. So the question I want to ask is, if I take some set of finite graphs increasing to some infinite graph G infinity, is there a percolation phase transition? As you vary beta, of course. And if there is, what are the properties of this transition? So any infinite graph G infinity and taking G and increasing is interesting. Well, any is too strong. If you take a tree, then you're just talking about percolation because there's no conditioning whatsoever. So we shouldn't take a tree because we already know what happens. So you should take something else. For me, the most interesting, or what I want to talk about today, is taking ZD and taking boxes approximating ZD. But you might like to think about other examples. So there's something a little bit tricky here, which is that this conditioning is extremely singular of bond percolation. So it's only really well defined on a finite graph, and it's not obvious at all what infinite volume object exists. So you can, of course, take subsequential limits, and just for the point of view of this discussion, I'm going to make the convention that I'm just considering translation invariant subsequential limits. And if this distresses you, let me say in advance, all results are going to be quantitative and finite volume, meaning that every infinite volume limit is going to inherit the properties that I prove. Okay, so once you decide to ask this question, what are the percolation properties of the arboreal gas, and you choose your favorite infinite graph that you're approximating, there's a few things that you can prove quite quickly. So one is that there's a stochastic domination of the arboreal gas by bond percolation. So that's this point number one here. And this is sort of easy to prove. It's just Hawley's inequality for stochastic domination. So what you learn is that if this parameter p beta, which is beta over 1 plus beta, is below the critical threshold for bond percolation, then there's no infinite tree or no infinite cluster. In particular, you learn something like the connection probability. So that's what I mean by this event, 0 double arrow to x. The probability that 0 is connected to x inside some component of the random forest decays exponentially in the distance to x. So you can easily prove that there's sort of some almost independent phase. And the next thing that you might want to do if you're familiar with bond percolation, which I suppose I'm implicitly assuming everyone here is somewhat familiar with, is that you can prove a sort of version of the Burton-Keane result, or you can use Burton-Keane's proof that there's almost surely going to be only 0 or 1 infinite trees. So if there is a percolation transition, then you're going to see at most 1 infinite tree. And it's here that I'm using this assumption that limits are translation invariant. Okay. So I should say, if there's questions, just interrupt me. There's no place that we have to get, so I'd rather you interrupt than
maybe
ask a
question, Tyler.
Sure.
So you're using Burton-Keane, and that requires some finite energy. So this is okay because you have a forest and not a tree, so you don't mind if you break.
Exactly. You can pick some ball and delete everything, and that's perfectly allowed.
All right, yeah. Perfect, thanks.
Okay, so I said I'm interested in ZD, but it might be easier to start with something with a little less structure. So let's start with the complete graph. This is a traditional thing to do, the mean field example. So I take Gn to be the complete graph on n vertices, and then this arboreal gas measure is just the Erdos-Renyi random graph conditioned to be acyclic, to have no cycles. So the conventional thing to do here, which is what makes sense, is that you should take beta to be proportional to 1 over n to make sure you see something interesting. And then there's the following theorem about what happens for the phase transition for the arboreal gas. Well, one, there is a phase transition. So if you look at the size of the tree containing some fixed vertex, so 0 is just some fixed vertex, and I look at its expected size, then I have a very clear transition. If alpha is less than 1, it's of constant size. If alpha is bigger than 1, it looks like a positive fraction of the vertices, some constant times n. And if you're exactly at alpha equals 1, then it looks like a constant times n to the 1/3. Okay, so alpha equals 1 is the critical point. And we see this difference in behavior. So above, there's percolation, there's a giant component, and below, there isn't. So this theorem is not our theorem. It goes back a way to Wuchek and Patel. And there's much more known about this, actually. There's a paper by James Martin and Dominic Yao that gives very delicate properties of what happens exactly at the critical point. So they sort of classify the scaling limit of the cluster sizes. So this might be, in some sense, discouraging because it looks like it's behaving exactly the same as Erdős-Rényi, and you would expect this conditioning to actually do something. I mean, it's a pretty severe conditioning. So it actually does do something. So one is that this constant in the supercritical case is actually different than from Erdős-Rényi. But there's a much more dramatic change, which is that if you look when alpha is bigger than 1, if you look at the second largest component, so not the giant tree, but the next biggest one, it has size n to the 2/3, which is sort of like the size of the critical tree, or the critical component size. So it's n to the 2/3 gives you the expectation n to the 1/3 because of the 1 over n when you take the expected size. And you should compare this to the Erdős-Rényi random graph, where the second largest component has size log n, which is the subcritical size. Okay, so there's something that's very different happening here, which is that once you go above criticality, you see one giant tree, but then you see many fairly large trees as well.
Why again is n to the 2/3 the critical tree size and not n to the 1/3? Could you say again?
So the expected size of the tree is n to the 1/3 if the size could be up to n to the 2/3. Because with probability, 1 over n, choose the vertex and you're in the giant n to the 2/3 with, yeah.
Okay.
Okay, so on the complete graph, maybe one other comment here is that alpha equals 1 is exactly the transition for Erdős-Rényi. So in some sense, not so much has changed in the arboreal gas compared to the Erdős-Rényi random graph. But in the supercritical behavior, you start to see some differences. Okay, so on the complete graph and on the tree, you still have a transition. It looks kind of like percolation in some sense. The main theorem that I want to tell you about today, which was with Roland and Nick and Andrew, is that this conditioning can have a very profound effect. So if you look at Z2, then no matter what beta is, there's no percolation. So unlike the complete graph where this conditioning just sort of changed some of the properties of the percolation, in the case of Z2, this conditioning just removes the existence of a transition. And in fact, what we prove is that if you look at the connection probability from 0 to x, it always decays polynomially in the distance. So this quantity C beta here is just some quantity that's greater than 0, and it depends on beta principle. Okay, so something dramatic has happened. Something has really changed. So for those who are random cluster model aficionados, let me make a little comment here, which is really taken from a paper of Deng, Garoni, and Sokol, which is that you could predict the fact that there's no transition on Z2 using exact, if not exactly proven formulas for the random cluster model. So for the random cluster model, it's known that the critical point is square root q over 1 plus square root q on Z2. And that's a theorem when q is at least 1, due to Bafara and Dumenil-Copin. It's not known when q is less than 1, but if you pretend it is, then it tells you that the critical point of the arboreal gas, beta c of q, looks like 1 over root q as q goes to 0. So that blows up. So that tells you there won't be a transition. But I have no idea how to make that into a theorem. because you would have to know in advance something about the critical point and its continuity as you go to 0 in Q.
Tyler, do
Yeah.
your arguments give anything for beta, which is large on the, I mean, so somehow trying to capture beta going to infinity. So the rate at which you have to take beta to infinity to actually.
I think you could get something out of it, but I can't sort of reconstruct what that is off the top of my head.
Sure, yeah, just wondering if
Yeah.
match the remark in some sense. I don't know what sense exactly.
Yeah, so I mean, this remark somehow is about Q going to 0, so I'm not sure how, I'm not sure how you would detect the remark, unfortunately,
yes.
in the behavior. Okay, so let me say up front that I think a very interesting question is to give a different proof of the theorem I'm telling you about. So in particular, a direct proof would be very interesting because I'm going to show you a proof, but it's rather indirect. Okay, so in the rest of the talk, what I want to do is tell you some conjectures about the behavior of the arboreal gas on ZD, because it has a lot of seemingly very interesting properties that we don't yet know how to prove, that are in some sense actually what motivated us to study it. So I'm going to tell you about those. And then I'm going to describe sort of the key new tool in our proof, which is something called a magic formula for connection probabilities. So this model, the arboreal gas under various names, has appeared in the physics literature, in the combinatorics literature in the past, and also in the random cluster model literature, but it hasn't really been studied very much because there's like a complete lack of tools. So I want to give you some idea of what we found. Okay, but first some conjectures. So one slide worth of conjectures. So the first one is that on Z2, what we're proving is actually very far from the truth. It should actually be the case that the connection probabilities always decay exponentially fast in the distance to x, not polynomially. Okay, so for every beta, there should be a positive m beta that tells you the rate of decay. If you like, this says that the phase transition at beta c equals infinity is sharp. And there's something quite subtle going on here, actually, because we think that this correlation length is actually exponentially small in beta, which is much smaller than if you go towards the critical point in something like bond percolation. So I don't want to get derailed into this, so let me just say that this is, the reason that this is very interesting is that this is the same behavior as for something like 40 Yang mills. So that's one of those problems where you get lots of money if you solve it. So this extremely small correlation length is symptomatic of several interesting problems, Yang-Mills, Anderson localization in 2D and things like this. And this is a very simple combinatorial model that seems to have the same property. And I think that's one reason that it's a very interesting thing to study. Okay, so that says that we've proven there's no transition in 2D, but we're very far from the truth. What happens in higher dimensions? Well, what we think happens is that in 3 and more dimensions, there is a transition. So there's some finite value of beta so that the connection probability is bounded below by a positive constant that depends on beta. So you will see a giant tree on Z3 and higher at finite beta. And in fact, something even stronger or more interesting should be true, which is that if you subtract Z beta and look at the fluctuations, they should be Gaussian. Okay, so if you subtract C beta, you should see this polynomial decay of connection probabilities. And here again, so for percolation, this is exponentially fast. So somehow the structure of what happens in the supercritical regime here is somewhat richer than happens in ordinary bond percolation. And roughly, this is due to large non-giant trees. Sort of like we saw in the Erdos-Renyi case, where there were these n to the 2/3 sized trees that weren't the giant. Here, we believe there's a unique infinite tree in the supercritical regime, but there are still sort of quite big, not infinite ones, and they're causing these Gaussian fluctuations. Okay, so one other conjecture that's rather different from the other ones that originates in combinatorics, which is that this is supposed to be a negatively correlated problem. So if you look at the probability that two edges E and F are in your forest, so that's this quantity here, it should be upper bounded by the product of the probabilities. So maybe a remark, it's known that if you put a 2 there, it's true. This is a recent result of Brandon and He, who were coming at it from an algebraic geometry point of view, motivated by very different things. Unfortunately, with this 2, it doesn't seem to be very useful probabilistically. You really need a 1 to make it probabilistically useful.
Do you see some such behavior for ZD already?
As in, do we know that this correlation conjecture is true?
Yes.
No. So knowing it's true on ZD would be quite interesting already, because it would tell you that if you take limits through finite boxes, you would have a unique translation invariant limit. But we don't know that.
Wait, this would imply uniqueness. Is this already clear?
Not exactly. It's sort of like the argument you use for constructing an infinite volume limit of the Ising model using Griffith's inequality. So there's a way to bootstrap this type of inequality to getting existence of the infinite volume limit and translation invariance.
Thanks.
But the uniqueness in any dimension or uniqueness in 2 dimensions?
So uniqueness in the sense of the percolation measure would look unique, like the measure on forests. The phase transition here is this infinite tree, finite tree, which is a bit different than asking about uniqueness for Ising.
Okay, very good.
Okay. Sorry, and it's only uniqueness when you like fixed boundary conditions, like free boundary conditions. I'm not saying
this is what I wasn't.
Yeah, I'm not saying across all boundary conditions.
So there is actually a comment which says that there's an earlier paper by Hu, Schroeter, and Wang which already shows this bound. I don't.
Oh, that could be true. So I learned about it from this paper of Brandon and He, but okay, thanks. So they work in a very general context, and this is just a particular example for them. Okay, so those are the conjectures, and basically they all seem quite interesting, but possibly difficult. It's not clear how to attack these. So let me give you maybe a touch of intuition for why this is happening. These behaviors that are quite different than, say, bond percolation. And I'll come back to this later as well. It's roughly that in bond percolation, if I look at the probability being 1, so sort of the full configuration, all the edges are open and there's a unique configuration. So in some sense, it's an extremely simple model once you take P extremely close to 1. For the arboreal gas, if you take beta to be infinity, well, this is actually very complicated still. if I look at a finite box and I take beta to infinity, I get the uniform measure on spanning trees. Right, so it's a uniform measure on spanning trees. There's exponentially many of those. So unlike bond percolation, which has this unique ground state, the arboreal gas has very, in some sense, disordered ground states. And this seems to influence the behavior at large beta. So that's a very rough explanation, and it's not something I know how to turn into a theorem or make precise, but we'll see a connection with spanning trees in a few minutes. So this is maybe a good thing to have in mind. And let me just reiterate, considering other families tending to some infinite graph is interesting, and I think people have not thought about it much, so there may be simpler settings in which analogs of these conjectures could be shown to be true, and it seems quite interesting to see if that can be established. Okay, so that's the conjectures part of the talk. So now what I want to do is give you some idea of the new tool that we have. So this is what we are calling a magic formula. It doesn't seem entirely appropriate to call a formula you derive yourself the magic formula. So what I want to explain in this slide is that it's not our name. People already gave it that name. So we're not doing something so absurd. Okay, so, oh, somehow this slide. Are you still seeing my screen?
I do see your screen, but it's the same slide with the conjectures.
Yeah, so somehow it's not scrolling. Sorry, I'll try and get it to show the right slide again. I'm not sure why it won't. 1 second. So maybe I'm just going to disconnect my screen and reshare.
No problem.
To try and fix this.
Now
okay. Okay, so now the comments about the spanning trees is there, but let's go on to the magic formula. Okay, so for me, delta is the graph Laplacian, so it just acts on functions on vertices by summing over all the neighbors, and then I stick in a beta, fj minus fi. So this is the ordinary graph Laplacian. And then the magic formula is this thing here. It's kind of long, so let's parse it together. It says that if I want to look at the probability 0 is connected to x in the arboreal gas, then up to some normalization that I haven't written down, you just have to compute this integral over Rn, and you get the answer. Okay, so let's do it a little more slowly because that's probably still too fast. So each t lives in R, and I'm integrating over Rn minus 1 because I fixed t at some fixed vertex 0 to be 0. And then what am I integrating? Well, it's e to the sum over all nearest neighbor edges, beta times cosh ti minus tj. There's a determinant of the Laplacian. So here I mean that I'm going to take the minor where I delete the row and column associated to 0, and I raise it to the power 3 over 2. And then I also have this density e to the minus 3t for each vertex. Okay. So it's kind of surprising that you can write a connection probability in this arboreal gas measure using this formula. And we certainly didn't just guess this.
Sorry, Tyler, where's the dependence on x in that formula?
Pardon me?
Matan, could you ask a bit more loudly? We can't hear you.
Sorry, can you hear me?
Now I can, yeah.
Bit better.
I was just wondering, where's the dependence on x in that formula?
It's here in this e to the tx.
Dx is...
So it's connection from 0 to x. The dependence on x is
okay,
in
okay,
e to
I
the
understand.
tx.
E to the x is, okay, cool.
Yeah, and the 0 is here in the pinning.
Thank you very much.
Yeah. Right. So like I said, we didn't guess this formula. I have a direct proof of this formula would be pretty interesting too. I don't know how you do that. But let me justify why it's called the magic formula. So if you replace the 3, this 3 here, and this 3 here with a 1, then this measure on the right-hand side is what's called the magic formula, or the mixing measure, for something called the vertex reinforced jump process. So this has showed up, I guess, quite a bit in the past, I don't know, 12, 15 years now, in the study of this reinforced process called the vertex reinforced jump process. So rather than going into the detour of exactly how to define the vertex reinforced jump process, let me tell you about its relative, the edge reinforced random walk, to give you some flavor of this connection. So the edge reinforced random walk, it's a discrete time walk on a graph where you start with some edge weights gamma on every edge. And you also keep track of NE, the number of times you've used an edge E up to time t. And then what this walk does is it's at some vertex and it sees some neighbors, maybe with N1, N2, and N3 crossings. And then it will take the edge with N2 crossings with probability proportional to gamma plus N2 over 3 gamma plus N1 plus N2 plus N3. So that's like the probability that you will do this. Okay, so this is a process that likes to reuse edges. The more it's used them in the past, and it increases how much it uses them in a linear way. Okay, so this was introduced by Diaconis in the 80s, and one of the first theorems about it was that it's actually a random walk in a random environment. So the edge reinforced random walk, this measure on the left here, you can rewrite it as choosing a random environment, C, and then running a random walk in that environment. Okay, and this thing d mu gamma is called the mixing measure and became called the magic formula for the edge reinforced random walk. And that's the vertex reinforced jump process is sort of a very similar thing that also has a magic formula. And the surprise here is that it's the same magic formula up to the fact that you change 1s to 3s. Okay, so this is the tool. This is the tool that we found that was useful for us in proving that there's no transition in 2 dimensions. So the next slide is a sketch of how you actually carry out the proof. So it has, I guess, 4 steps in the way that I've drawn it here. The first step is to take the arboreal gas, which is just this combinatorial quantity, and you rewrite it using some version of the matrix tree theorem as something called the H02 spin model. I'll show you how to do this in just a second. The next step is to convert the H02 spin model to something even slightly more exotic called the H24 spin model using a trick called dimensional reduction or supersymmetric localization, both of which sound somewhat scarier than it really is. So those 2 steps are basically identities. That's why these arrows go both ways. The next step is to make a great choice of coordinates called horospherical coordinates that were found by, or sort of introduced in this field by Martin Zirnbauer. And then you compute a certain marginal, and that actually gives you this magic formula. So that gives you this connection probability formula. And then the last step is to prove a Mermin-Wagner theorem, which tells you that there's no percolation. The last step is sort of an analytic step where you actually make an estimate. The first three parts are basically identities. Okay, so one remark is that the magic part is the vertical steps, the dimensional reduction and horospherical coordinates. And it's exactly the same magic as it is for the vertex reinforced jump process and edge reinforced random walk. So there's something more general going on with spin models of this type, where you seem to end up with these amazing formulas for probabilistic quantities in terms of these measures involving some powers of determinants of the Laplacian. I think from this sketch, you'll now believe my initial claim that our proof is somewhat indirect. So, you know, this is the challenge. How do you avoid this? How do you avoid doing this and instead do this? Okay. Okay, so I don't have time to go into all of the details of all of the steps. So what I'd like to do is try and explain the first step in some amount of detail in a way that can be followed and hopefully make some of it more accessible. And then if there's time, I'll say one or two words about the other steps. Okay. So remember, when beta equals infinity, the arboreal gas becomes the uniform spanning tree. So if we take a finite graph and we take beta to infinity, the measure concentrates on spanning trees. And one of the things that you learn about spanning trees is that you can count them by computing a determinant of a minor of the Laplacian. So that's the matrix tree theorem. And you also learn at some point, or you may have learned at some point, that they're a determinantal process. And physicists would describe that by saying that it means that uniform spanning trees are a model of free fermions. So what I want to do is show you what that means in terms of fermions, in terms of anti-commuting variables that play the role of what physicists call fermions, and then show you how you get this H02 model and the relation to the arboreal gas using that terminology, that language. So this is a bit of a shift of gears from sort of giving you these conjectures and showing you a big formula to really saying, I'm going to tell you all the rules to compute fermionic integrals and do this calculus. So let's start by rewriting the matrix tree theorem in terms of fermions. So to do that, we need to have those objects. So what are they? If I have an n vertex graph, I'm going to take two n variables, and I'm going to call them xi1 up to xi(n) and eta1 up to eta(n). And they're going to have the property that they're anti-commuting. Okay, so what does that mean? It just means, well, it means what it says. Xi eta j is minus eta j xi I, eta I eta j is minus eta j eta I, and xi I xi j is minus xi j xi I. So they all anti-commute with one another. So in particular, the square of xi I is the square of eta I is 0 for all I. Okay, so these are just some symbols, and I've said they have to satisfy this relation. And what you can do then is you can ask, you can form the algebra that satisfies these relations. It's called a Grassmann algebra. So all it means is that you look at linear combinations of products of these generators where the coefficients are real numbers. Okay, so an example of an element of the Grassmann algebra is 3 xi1 eta 2 plus 7 plus xi1 xi3 eta 5. Okay, and all of these objects are going to be polynomials of a maximum possible degree, because if I ever take the square of something, I get 0. Okay. So it's just this collection of polynomials. And once you have that, you can introduce a derivative. Why not? If I take some element f, if I take some element f, that's a monomial, so just some product of the xi's and etas, and let's assume it doesn't contain xi I, then I define the derivative with respect to xi I of xi I times f to be f. So that looks like the derivative, right? Partial xi I is killing the xi I. And otherwise, the derivative is 0 because it doesn't find a xi I to annihilate. Okay, then you extend this to be an operation on the whole algebra by linearity. So if I have some linear combination and I apply xi I to it, I just apply xi I to each piece individually. And if I ever want to kill a xi I inside, I just have to bring it to the front of the expression so I can use this rule. And as you bring it to the front, you might pick up some minus signs because of the anti-commutation. So all that means is that partial xi I is an anti-derivation. Okay, so that's how you take a derivative. Here's the reason that that's a good thing to do. This exercise is the thing that should convince you that this is a pretty interesting algebraic structure. So if you take any n by n matrix A and you want to compute its determinant, here's a formula to do that. You just take this derivative. So with respect to all of the generators, partial eta 1, partial xi 1, all the way up to partial eta n, partial xi n, of this element of the algebra, exponential of this sum. So what does that mean exactly? Because before we had these finite linear combinations, and now I've all of a sudden introduced an exponential function. So what I mean is that you Taylor expand. So when you Taylor expand the exponential, you just get a sum of powers of the argument. And that's going to truncate at some finite order. Because if you ever take 2 xi i's or 2 eta i's, you get 0. So expanding this makes perfect sense as a polynomial, and it even makes sense in terms of the anti-commutation relations. You don't have to worry about the order because this element here is commuting. Because it has xi I times eta j. So if I moved some other generator from here to here, I would have to pass through 2 terms, so I get 2 minus signs. So there's no problems with understanding the order of the multiplications when you expand this term. Okay, so again, what happens? If you want to compute the determinant of any n by n matrix A, you can form an element of the Grassmann algebra by this rule and compute this derivative, and you get the determinant. Okay, once you work it out as it is an exercise, and you see that you just exactly rebuild the definition of the determinant. So let me say, sometimes this thing here is called the fermionic Gaussian free field. And the reason for that is you should compare it to the ordinary Gaussian free field or 2-component Gaussian free field, where if you had a positive definite matrix A, you could compute 1 over the determinant of A by computing this Gaussian integral. Okay, so now that we have that, let's think about the matrix tree theorem. So the matrix tree theorem, when you're counting spanning trees, is something about the Laplacian. So I want to take something that looks like the Laplacian, and I'm going to multiply it by beta, so that I get a weight of beta for every edge. And I'm going to take H to be some diagonal matrix. So A is some matrix then, and the matrix tree theorem says the following. It says that if I compute, well, what's the left-hand side? The left-hand side is this fermionic integral. But the fermionic integral is exactly this derivative that I introduced on the previous slide. So sorry to go back and forth here, but this operation of taking this derivative is called fermionic integration. Okay, it's slightly weird to call a derivative an integral, but that's what we do. And this quantity in the exponent is exactly the exponential expression on the previous slide. On the right-hand side, what we have is a sum over rooted spanning forests. So that means that it's a forest, and in every tree you have a designated vertex called the root vertex. And then for every root vertex, you pick up a weight of the root, and you get a beta per edge. So this might not look exactly like the matrix tree theorem that you're most familiar with. It's sometimes called the all-minors matrix tree theorem. And just to see that the one you're more familiar with is basically a special case, what happens if we take the diagonal matrix H to be non-zero at just one entry? So take H to be the indicator that I is some fixed vertex 0. Well, then the set of forests with one root is exactly the same as the set of spanning trees, because if every tree must have exactly one root in it, having only one possible place where the root weight is non-zero restricts you to having trees. Okay, so what this says is that the fermionic Gaussian free field, this combination e to the minus eta a xi, encodes rooted spanning forests, and in a special case that encodes spanning trees. And it's important to realize that rooted spanning forests and spanning forests, like the arboreal gas, are very different. Because if you wanted to get a measure just on spanning forests from the rooted spanning forests, you would have to sum over all the possible roots, and this would introduce an additional weight per tree. So somehow the fundamental observation, if you want to study unrooted spanning forests or the arboreal gas, it goes back to Caracciolo and co-authors, who were really the big inspiration for us when we got into this, which is the following. If you take H to be the diagonal matrix of all ones, then you can get the measure on unrooted spanning forests by adding something into the fermionic integral. So you add in a term where you sum over all edges, xi I, eta I, xi j, eta j. So this thing here. So what's happened is that you have replaced the fermionic Gaussian free field and you've put in an additional interaction term. And what they proved is that then you get exactly the sum over all spanning forests with no rooting. So why does that happen? Well, this term, roots at vertices, that's the matrix tree theorem, and this term, roots at edges, with a -1. So since in every single tree, the number of vertices minus the number of edges equals 1, once you sum over all the possible roots, you end up with the sum over unrooted spanning forests. So it's not that what I just said is a proof, but that's what the proof shows is true. Okay, so this is sort of this sort of nonlinear matrix tree theorem, which is an interesting formula, but it's important to reformulate it to sort of make use of it. And it's the reformulation that shows some connection to hyperbolic symmetry. So they thought about it in terms of a sphere, but I want to tell you about how it looks like hyperbolic space. So I realize I'm almost out of time, so I'm just going to reformulate it, and then we'll stop there. So this is what you do. You introduce some new objects. So in this algebra, you define an element zi to be 1 minus psi I eta I. And you introduce at every vertex this triple, which is you think about as being the spin at I. So it's psi I eta I zi. And you introduce an inner product, ui dot uj, by this formula, minus psi I eta j minus psi j eta I minus zi cj. Then you check ui dot ui is minus 1. So this is exactly what you get if you find that, if you look at the hyperboloid model of hyperbolic space in Minkowski space. So what's happening here is it's just imitating the algebraic formulation of how to study hyperbolic space or the hyperbolic plane. And if you do that, what you learn is that you can rewrite this quantity here in the following way. You instead have u inner product with the Laplacian u, like for a Gaussian, and you also have to insert sort of the analog of Haar measure, 1 over z. And then this quantity here is exactly this quantity here. So for these hyperbolic spins, you have a representation of the sum over unrooted spanning forest. And the reason that you should become convinced that this is really a good idea is that if you go through the same computations and ask what's the probability a vertex I is connected to a vertex j in a random spanning forest or in the arboreal gas, it's exactly the expected value of the inner product between ui and uj in this reformulation. Okay, so this inner product here is not a probabilistic inner product, or not a probabilistic expectation. It's a fermionic expectation, but it gives you something that looks more like spin models, like the Ising model that we're familiar with. So this is what I meant by the H02 model has a graphical representation in terms of spanning forces.
Tyler?
Yeah.
When you write 0,2, this is to say that the integration is purely fermionic with two Grassmann variables per site?
Exactly. So 0,2 means 0 commuting variables. And it means 2 anti-commuting variables. Yeah. Okay, so I think I'm out of time, so I can't really show you the other steps.
Tyler, you still have, we run for an hour, so you still have 4 if you'd like, meaning 6 more minutes.
Okay, so maybe I just will say this then. I'll skip step 2. So step 2 is this dimensional reduction step to convert H02 to H24. Step 3 is sort of maybe we'll connect it to maybe a more familiar thing. So as I was just saying that H02, we found this sort of hyperbolic type algebra inside. So here's recalling what happens for ordinary hyperbolic space. So H2 is ordinary hyperbolic space. And you can describe it by taking triples of real numbers, x, y, z, satisfying the equation x squared plus y squared minus z squared is -1, and z is positive. So if you like, this is exactly saying that ui dot ui is -1 if you use this definition of the inner product. Okay, so that's a way to construct the hyperbolic plane, looking at this set with the induced metric. So the good coordinates are called horospherical coordinates, and they're given by the following equations. So the hyperbolic plane is a two-dimensional manifold. So using 3 coordinates x, y, z to parameterize it is a bit redundant. You might want to find a way to do it with just 2. And you can do it using 2 variables s and t in R, where you define x to be sinh t minus 1/2 s squared e to the t, y is s e to the t, and z is cos t plus 1/2 s squared e to the t. And then you can check that you can rewrite this inner product here in terms of those variables in a very nice way, like this. So the inner product between ui and uj in this case is just cosh of the difference in t's plus 1/2 si sj e to the t out of tj minus 1. So why is this useful? It's useful because here it's a quadratic expression in the s's. So what that means is that you can integrate over the s's easily because it's a Gaussian integral. So that's what's happening also for this magic formula. So for this H24 model, which is roughly defined like the H02 model, there's a similarly good choice of coordinates. And then you can integrate out all the variables except for the t's, because they're all Gaussian integrals or fermionic Gaussian integrals. And you're just left with this nice measure on the t's, which is where this power of the determinant came from in this magic formula. So that's the origin of this term. It's coming from computing Gaussian integrals, leaving you with the t's. Okay, so I think I'll stop there.
Thank you very much, Tyler. Very well presented. So if anybody wants to ask a question, please unmute yourselves and ask.
So your magic formula does not have anything to do with Z2. Is that correct?
That's right. It holds on every graph, every finite graph.
Every.
Yeah, it's just a general identity.
Tyler, let me ask, you said that the next step, the one you didn't get to say anything about, is a Mermin-Wagner step.
Mm-hmm.
And I remember that one complication in these models for doing Mermin-Wagner is to understand something about large edges. I mean, edges where the difference ti minus tj happens to be large. Do you get such a complication in your approach or not so much?
Yeah, I guess it's the case that there's now sort of 3 distinct Mermin-Wagner proofs for the vertex reinforced jump process. And I have to admit that the 2 that we thought about are not the one that you gave with Gaddy. So in some sense, we don't see that so explicitly. But it would be interesting to see other ways of proving Mermin-Wagner theorems, or maybe you have to deal with that. In particular, for the edge reinforced random walk, there's sort of a direct Mermin-Wagner theorem just in terms of the edge reinforced random walk. And here we don't have anything like that in terms of directly in terms of the forests. So there's something interesting going on in terms of the geometry of the forests that prevent there from being a transition, but we don't really have an idea of how to capture that probabilistically. As in what is the spin wave when you look at the forest? I don't know. We just adapted Christophe Sabot's proof for the vertex reinforced jump process to this case, and it works.
Okay, thanks. Other questions?
Tyler, so I have a question. So when you introduce this, unrooted version of the integral, so why would that interaction term, you said it's like a rooted on the edges? It seems to me like it's some nearest neighbor in the product kind of.
Right, so you're saying, why does this term root on edges?
Yeah.
Yeah, so the way to think about it is that if you want, you think about the ordinary matrix tree theorem. It also gives you formulas for moments. And the moments tell you certain connections in the tree. And what's happening here is that you're saying that there's going to be two trees, one rooted at I and one rooted at J. So in particular, actually the edge IJ won't be present, but then because of this beta here, you can pretend that they're actually joined. So that's how it sort of gets rooted at an edge.
So it's actually rooted at sorry, both I and J as you.
Yeah, so it's actually that you're summing over all edges and rooting at both endpoints of the edge and ensuring that the weight is actually there. But I think the right way to think about that is saying, well, you've rooted it at the edge. So it's not quite like an inner product in the sense that the inner product should mix. This thing here is the natural inner product in the problem. It's not the product of the sides along the edge.
Right, okay.
I'm not sure that's a satisfying explanation, but when you carry out the proof, if you carry, you can also prove it just using symmetries of the H02 model, that this representation is true. But if you carry out sort of the algebraic proof using the matrix tree theorem, then that's what this does.
All right, thanks.
Are there other questions? I had one more, Tyler.
Mm-hmm.
I heard Nick talk about related things, and I remember he mentioned other models which have the magic formula similar to the one you showed, but with the number 3 replaced by other numbers.
Yeah.
Could you comment on that?
Yeah, so if you replace, there's also these, let me maybe make it red to make it more visible. If you instead look at the H02N model, then you again get a magic formula, and this parameter A that was 1 for the VRJP or 3 for the spanning forest becomes, I guess it must be, well, you can get other odd powers of odd A, however you linearly convert in that way. So the VRJP is H22, and somehow the number A that shows up is something like 2n minus A. Or
and these other models also have some like VRJP or arboreal gas interpretation?
so they seem to, but they don't seem to have quite as, there's nothing I can say definitively now, I think is the fair thing to say. But I believe that there are such interpretations.
Okay, other questions? Okay, if not, then let us thank Tyler again for an excellent talk. And usually we stay somewhat informally, so I'll stop the recording now, and anybody who wants to talk informally is quite welcome.